Hello, everyone. Welcome. Today we have Maya, a senior data scientist at Mendeley, giving a talk on sparkling science up with research recommendations. So please help me welcome her.
Hi, can you hear me? Yeah, I think so. My name is Maya. I work on the data science team at Mendeley, and today I'm going to talk to you about our article recommender that's called Mendeley Suggest. And then in particular, I'm going to go into quite a bit of detail of the computation layer. How do we actually go about generating these recommendations? What are the algorithms and implementations we've considered, and how does Spark fit into it? So what is Mendeley? At Mendeley, we build tools for researchers, and we help them organize and read research articles, collaborate and network with one another, as well as, in particular, search and discover relevant articles. And that's the use case I'm going to talk about today. So keeping up to date and discovering research articles, it's quite important for researchers. It takes a lot of time. There's a ton of research being produced each year and then over time. And one of the main use cases we try to help researchers with on the data science team at Mendeley is helping them keep up to date and discover relevant research articles. And one of the tools we've built for that is what we call Mendeley Suggest, and it's our personalized article recommender. And essentially, what it does is it looks into users' libraries and then recommends, here are other related articles or relevant research that you may want to look and read as well. So when we talk about recommender systems, oftentimes, especially in data science forums, we talk about the algorithms, the data, and the features. And that's great, and that's a lot of fun. But to build a recommender system, I just wanted to point out that there are two other quite important components that oftentimes we don't talk about is getting the business logic right, and that getting the UI and the right user experience is equally as important. So getting all of these four components in sync is extremely important in order to be able to get the best user experience and to deliver the most value to the user. In this talk, I will talk about the algorithms mostly, but I just wanted to kind of give a sense that oftentimes when we talk about recommender systems at Mendeley or any majority of time in recommender system conferences, we cover all four of these components, and it's important. So Mendeley Suggest, we built that a couple of years ago, and it started as a Hadoop. It was built on top of Hadoop. We started off with native Java MapReduce, and over time we moved into cascading, and more recently into scouting. And the core component has quite often been, for quite some time actually now, has been on Mahout. Recently, in the past couple of months, this year, we've moved our data and feature engineering into Spark, and our business logic into Spark, but we still have our component of the algorithm being powered by Apache Mahout. And so we have this now mixed stack of some components are in Spark, some components are in Hadoop, and ideally what we'd like to see is a more consistent stack of Spark, say, powering the whole pipeline of the batch processing, makes it easier to deploy and maintain, and we no longer have to look at native Java MapReduce code, which is what Mahout is implemented in. So I'm now going to go into a bit more detail around, well, what are the algorithms that we've tested with and implemented as part of the computation layer, and then I'll talk about how we evaluate and how they perform. So the setup is we're doing a personalized article recommender. We have our user libraries, which is the input, and then we're trying to produce the output is a list of suggested articles. There are a number of different algorithms you can use. You can go for content-based or collaborative filtering solutions. In this talk, I will talk about collaborative filtering solutions, and in particular, I'm going to talk about three types of algorithms: item-based, user-based, and matrix factorization. So just briefly, item-based collaborative filtering, the idea there is to find items that are similar to the ones you already have in your library and then to recommend them, very much like Amazon style of users who bought this also bought that. User-based collaborative filtering is very similar, but rather than doing items that are finding similar items, you're looking for similar users. So you look for users with whom you have a lot of overlap in what you read, and then based on what else, you look at what else they're reading, and then you recommend that to the user. And matrix factorization, that's oftentimes when people talk about collaborative filtering, they immediately think of matrix factorization. That's the most, it got quite popular around the Netflix competition. But the idea there is you have your user item library and you build a model, which consists of the lower dimensional representation of the users and the items. And then based on that, you can make predictions on new items for the user by taking the dot product of the user vector and the item vector. So we have these three algorithms. We want to compare them. We want to see how they perform. So we need to evaluate them. In this talk, I'm going to focus on two dimensions, the runtime and then the quality. And ideally, we don't want algorithms that take a long time to run and the quality is not as good. And we want to be in this corner, in the lower right corner. We want them to be as good as possible. And then if they don't take too much to run, they tend to be cheaper for us. How do we measure quality? Well, oftentimes in machine learning recommender systems, we do offline evaluation. You have your ground truth data set, and you then compute metrics on it. When we talk about offline evaluation, oftentimes we do cross-validation. In recommender systems, what we also do is what we call time-based validation. So rather than leaving out a random subset to test on, you split on time. So you train up to time t, and then from time t plus 1 onwards is when you test. And then when we compute metrics, oftentimes we look at metrics such as precision, recall, or ranking measures such as normalized discounted cumulative gain, or NDCG, among others. So we have our evaluation and then the implementation. So there are a number of different implementations out there of these algorithms. There is Apache Hadoop, of Apache Mahout Hadoop. And then there is Spark. Spark MLlib comes with a number of implementations. And then over time, we've also dabbled on our own in some of them as well. So I'll go briefly into each one of those. The setup, all of them were tested on the same cluster. We spin up an EMR cluster, and the data that we used was user libraries, a subset of them. So we took 1 million users, a random sample of 1 million users, took their libraries, and that resulted in about 15 million documents. So note here that the number of items is a lot larger than the number of users. So we have this kind of short and fat matrix, whereas a lot of times when people talk about recommender system, the use cases, they have a lot more users than they have items. So that's kind of like the tall, and we call these tall and skinny matrices. So because of that, certain algorithms work better than others in our use case, than contrary to what you see oftentimes in the literature, and I'll go over that. For all of the experiments, we use time-based evaluation, and then we compare them based on precision at 10. So of the top 10 recommendations, how many did we actually get correct? So I'll first give a brief, just quickly go over the current Hadoop implementations that we're using. It's still what we use in production. We hope soon to be move that onto Spark. Will make everybody a lot happier. So Hadoop Mahout out of the box comes with item-based collaborative filtering and with ALS matrix factorization. And over time, we've also added a user-based collaborative filtering implementation on top of Mahout at Mendeley. So when we first started and we ran Mahout on the subset of the data, it was item-based, performed, it gave us a point. And then over time, we started looking into it, and then it wasn't efficiently optimizing or utilizing the mappers or the reducers. We had stragglers, so we spent quite a bit of time tuning and optimizing it by allocating more tasks, by using a better partitioner, by just optimizing it quite a bit and tuning it. And that gave us about 60% improvement in performance. So that was we were quite happy. It cost us a lot less. And then if you think about it, we have an item-item matrix. It's 15 million by 15 million on just this subset, which is about actually a fifth of our full data set. And the data set keeps growing. So we actually need, like, in reality, when we are computing this in production, we're talking about 60 million by 60 million matrices that we're computing. And so what we've looked at is when you do item-item similarity, a lot of the time was taken to compute the similarities. So, and when we look at it, when we transpose the problem and you look at the user-user matrix, or the user-user similarity, it's actually a lot smaller problem to solve. It's like we're looking at 1 to 5 million on each dimension, and it's making it a lot more tangible and feasible. So that's what motivated us to actually implement user-based collaborative filtering on top of Mahout. It was quite simple, and we could reuse a lot of the code that was already there. And for us, what surprised us was that it not only did it give us better performance in runtime, but it also gave us better performance in quality. And oftentimes, when we read the recommender system literature, item-based is the one that performs better than user-based. And for us, it surprised us that actually, by trying out a different algorithm, we managed to get gains both in quality and in runtime. And that's what we are actually using at the moment in production, the user-based. Item-based collaborative filtering still has its use cases, and some of our recommenders still use that. So we're very much interested in having scalable solutions for both of them. But just keep in mind, depending on your data, some solutions might be better than others. So what we learned, Mahout out of the box is quite optimized and already quite efficient, but depending on your data, by tuning, you can get quite a bit of improvement, and then by understanding your data and using the right type of algorithm, you can actually get even further improvement. So with all of that learned over the years, we now started looking into Spark, and we want to move this native Java MapReduce code into Spark, makes it easier. It should be a lot shorter to implement. Mahout came up with a Spark implementation of item-based and user-based collaborative filtering about a year ago, and we tested it. It's quite simple. It provides functionality to be able to compute the item-item similarity and the user-user similarities. However, unlike the Java Hadoop implementation, it doesn't go the extra step and actually producing the recommendation themselves. So once you have the similarities, you would need to take that and produce the recommendations. They provide it for real time, but in our case, we need to compute them in batch in order to be able to evaluate the user. So unfortunately, we spent quite a bit of time trying to get that to run, and we kind of had quite a few hurdles, kept optimizing, kept changing some of the parameters, increasing more of the level of parallelism, changing the way memory was allocated. And each one of these tunings, or each one of these parameters took us further and further, but we never actually got it to run fully on our data. So that was a bit disappointing, especially since when we've tested it on the MovieLens dataset, which is a standard benchmarking dataset in recommender systems, but even the largest MovieLens dataset is about, I think, 25,000 items to 200,000, 150,000 users. So it's still, compared to our scale, it's quite a bit smaller, but it gave the best performance. So again, it depends on your data. This might still be a very viable solution. We just didn't manage to get it to run. So on one of our hack days, I have to explain to our engineers quite often how does collaborative filtering work, item-based, user-based, matrix factorization. So and we all were trying to learn Spark. So we were like, OK, so let's give it a go and try to implement it. It's not that complicated to implement in terms of just the algorithm itself. And the idea there is, well, you need to compute the similarities. You compute the item-item or the user-user similarity. And then given the similarities and the user preferences, you can compute the recommendations. So how do we do that? I've included a code for completeness. I'm not going to go into detail into each of the lines, but it's quite simple and straightforward. So to compute, I've done the item-based collaborative filtering. To do user-based collaborative filtering, it's just as simple, and the code is just as short for it. But the idea there is we're going to compute cosine similarity between items. So you first take your matrix, and you take the norms of the item vectors, and you compute them. Broadcasting that did give us big improvements, so go broadcast variables. Then once you have the norms of the vectors, you can also do the dot product, take the co-occurrences and the dot product between the item vectors. And once you have both of these, then you can compute cosine similarity. And then you can take the top similarities. So that gave us the matrix of similarities for the items. And then once we have the item similarities and the ratings, we can multiply the two matrices and get the recommendations out. One thing to notice, do not forget to filter items the user already has, because oftentimes, well, one of the mistakes I've seen sometimes is when you actually end up recommending things the user already has. It's not very good user experience. And the filtering of the recommendations, currently this piece of code, it spends quite a bit of time on it, so that's probably one of the first places we need to optimize a bit further on our end. So how does it perform? Great, we've implemented it. Our first go with running item-based collaborative filtering on Spark, it ran for about 12 hours, and then it failed, so we were kind of sad. And then for user-based Spark, it finished, so that was quite exciting. One of them finished, but it wasn't quite as good as our very tuned and optimized Mahout implementation. But it still wasn't that far off, so it was like we were like feeling optimistic. We can actually, by tuning it, optimizing the code, we can get further. And we did. So by going through the code and making certain, understanding better where time was spent, where it was doing more shuffling, maybe more garbage collection, optimizing the code further, we got quite a bit of an improvement, but also looking into more of how are we actually setting up the number of executors, the number of nodes on each executor, the memory allocated, the level of parallelism, the resource allocation in terms of memory. It gave us like even further improvement. And so what we were able to do, and we're quite happy with, is we have now a moderately, I'll say, tuned version of user-based Spark that is performing better than our Mahout. It's not bounds and leaps better, but there is probably still a lot of room for optimization in the code that we continue working on it. And then with the tune item-based Spark, we got quite a bit. We were happy that we were able to have an implementation that gives us good performance. So what we learned is, well, yes, we can get Spark to scale to our data, so that was good. By this blog by Cloudera, so big shout out, on how do you tune Spark and how do you, especially around how do you set up your cluster, the resource allocation, the parallelism. It really helped us get these extra bits of performance out. And well, how about Spark already comes with a machine learning library, and they have collaborative filtering implemented in it, especially matrix factorization. And then also, like, they have some functionality there that can be used to compute item-based and user-based collaborative filtering. So we looked into that as well. Oh, just to note here, for matrix factorization on Hadoop, actually we never, I forgot to mention that, we never got that to run on our data. We've gotten it to run on sample data sets, or much smaller, but it never actually completed on our full data set. So we'll see how Spark performs. So for doing the user-based and item-based collaborative filtering, MOLIP comes with an O-pair similarities implementation of an algorithm called DIMSUM, which was open sourced by Twitter. There is the paper. You can go and read about it. But essentially, it's a very efficient way to compute matrix similarity, especially when you have a denser matrix. In our case, our data is quite sparse, but it was good to see, well, how would that perform? It only supports cosine similarity, so if you want to try different kind of similarity functions, it would either need to be extended or you would need to implement your own, but cosine similarity is good, so it's good to at least give it a go and to try it. It doesn't generate the actual recommendations, so it gives you the similarities, so in this case, we use the code that I showed before for computing the recommendations. It's really simple to use. So you can read you need to read in your data as a row matrix. So you can, and then you compute on the row matrix column similarities. So if we're computing item-item similarity, the items then need to be the columns. And then if we're computing user-user similarity, then the users need to be the columns. So you just need to read your data as a transpose or read it in a matrix and then transpose it. So that, with these 2 lines of code, that saved us, well, the 1 page of code that I was showing before for computing similarities. So if this scales, then it's making the implementation of the nearest neighbor algorithms even shorter and simpler, easier to maintain. We were quite happy to see that actually out of the box, it performed about the same as the version that we had tuned quite a bit. And that was good. We didn't quite get the big improvements from the threshold and the sparsity. And I think that's part of the reason is because it tends to really do much better on denser matrices. And in our case, our matrix is actually quite sparse. But that was good, so we can use that instead. And then finally, the matrix factorization, which most people, like when they try collaborative filtering, they go for that. Idea is you compute your model, and now as part of Spark 1.4, there is a recommend products for users. So you can actually, given the user and item representations in the model, you can then say, well, generate recommendations for all users for all items. That's quite a challenge, given that we have, well, for this data set, we had 15 million items. And then in the real data set, that's going to be about 60 million. But we were like, well, let's give it a go, see how that does. And then you need to filter the predictions. So to our surprise, matrix factorization did not perform as well as we can get with user-based collaborative filtering. This is with 500 factors. So arguably, and we could see that as you keep increasing the number of factors, the performance improves. We were not quite able to run more than 500 factors on the cluster we had. It kept running out of disk space. It's something that we could probably, we're working on and trying to further tune and optimize. And we'd really like to see how far we can push matrix factorization. It's supposed to be really the solution to it all. And then generating the model actually is not very slow. It's quite fast. The bump in the runtime cost that we see here is because of generating the recommendations. So we want to be able to generate the recommendations offline. It's not really realistic to expect that if you have 15 million items or 60 million items, you're going to be able to do this in real time when the user comes in. So we want to have these pre-computed, and pre-computing them is quite expensive. There are approximation techniques that you can use to speed it up, such as you can do some clustering on the items, or you can do locality-sensitive hashing to narrow down the amount of items that you're going to compute recommendations for. But these are approximations, and they can only actually hurt the quality. So even if I bring down the cost, the runtime, it's still going to be quite, that's not going to help us with quality. So what we're at the moment looking at quite extensively is how can we actually both improve the quality and speed up the computation, and then see how far can we push it, and is it really that for our use case, for our data, user-based collaborative filtering is the better option. To summarize, MOLIP with DIMSUM gave us a good alternative to being able to do user-based collaborative filtering. We actually, I didn't mention, we didn't manage to run item-item similarity with DIMSUM. And one of the reasons was it was trying to serialize an object that's larger than 2 gigabytes, and then it would fail. But when we tried to increase the maximum number, the maximum Creo serializer buffer to more than 2 gigabytes, at least when we tested it about a month and a half, 2 ago, it seemed to be hard-coded boundary to you can do more than 2 gigabytes. So I think as that gets worked on, that's probably going to go away, and it's something we'll come back to and test. And we still need a scalable solution for generating recommendations based on ALS collaborative filtering for our use case. So to sum up, running out of time, is if you, by tuning, we can get big speedups on the performance, and but for that you really need to dig deeper. You need to understand how the algorithms work, and sometimes it just means like drilling down into the code of MOLIP or Mahout or whatever that library is. And so understanding what it's implemented is crucial. And then by understanding your data and choosing the right algorithm for it, you can get big speedups in quality as well. So we have achieved our goal of having a Spark implementation that is on par or better than our existing Hadoop implementation of our collaborative filtering algorithms. So that's quite good. We're happy with that. And I think I've mentioned most of these points, and I want to leave some time for questions. So thank you.
Okay, so time for a couple questions.
Thank you. It's a very good presentation. So I have 2 questions. The first one is you use user-based recommendations. So I wonder, how do you solve the cold start problem for the new users? The second question is about, besides the top 10 precisions, do you use other metrics, for example, the coverage or the popularity?
So for these were mostly, when we use collaborative filtering, we are aimed at the existing users. So that's not for the cold start. So this is like, in order for us to evaluate, it's like, well, what would the user read next or add to their library next? For code start recommendations, we still use, what's popular, what's trending. Another algorithm is content-based solutions work quite well. For code start, they don't perform as well if you already have some usage data. That's what we find in practice, and collaborative filtering tends to be better for that. But for the code start, we use popularity, trending, and content-based solutions quite extensively. Also, item-item similarity is quite helpful when you have code start. So if the user just adds one article, then you can immediately start recommending them things that are already related to that. In terms of other metrics, yes, we look at a number of different metrics. Precision at 10 is by far not the only metric we look at. So we look at a lot around diversity, the coverage of the catalog, coverage of the users, and then it depends on the algorithm. For some algorithms, we use different set of metrics for different algorithms. So that depends. And oftentimes, these are all offline metrics. We evaluate offline. But then we also test these algorithms online on live traffic. And then we're very interested to see, well, can we correlate offline and online performance? Because if the two don't correlate, then our offline experiments are not really meaningful. Then they're not helping us build the best product we can.
Okay, one more question.
So first of all, thank you, very interesting presentation. And my question is, you mentioned that when you increase the rank, the number of dimensions, the quality increased. And I'm curious about the exact relationship, how many options have you tested, and was it real linear increase, and how did this behave? For example, 50 or 60 dimensions compared to 500.
So it's not quite linear. It's more like it goes up and then it starts to level off. So for example, between 300 and 500, we saw it like leveling off. So I'm not sure if I were to be able to push it to say 1,000, if I'm gonna get much more. We actually found tuning the other parameters quite a bit also more helpful. Alpha parameter in particular for implicit matrix factorization was quite significant for us to tune. The default value that comes with ALS was no way in the ballpark figure. I think we ended up going for like 50 or 60, and possibly we could even push it further. So yeah, like do test a wide range. With 50 factors, the performance was practically popularity. That's kind of what we see. So that's on the ballpark.
All right, that's all the time we have. So please join me in thanking one more time our speaker.